Interesting.
For the sake of the recording, welcome everyone. It's a pleasure to have here Bryce again. Most of you know Bryce because either support his programs or try to observe his program or scream at him because the program was complicated to be completed. But we are always
Or read many of his papers.
or yeah, be on some of his papers. So
All right,
it's a pleasure. Bryce got his PhD in 2018 at the Université de la Côte d'Azur. And then he moved around a little bit. He went to Washington, to California, to the California Institute of Technology, and was a NASA fellow of the Goddard Space Flight Center. And now you are a research scientist at Eureka Scientific. If people that are not familiar with Bryce's research, he is an expert of ESO-moon, ESO, everything, satellite, asteroids, and everything that sort of moves in the sky. This is your guy. So without further ado, please, the stage is yours.
Thank you. Thank you for the introduction. It's a pleasure to be here. I just wanted to give you all a kind of a brief update on some science projects that I'm doing with the Gemini North Observatory. And there might be some bonus content in here as well, but I'm going to click here to move the slide advance forward. Okay, so that seems to be working. So the talk is going to be divided into two talks. It's going to be two subtalks. This talk one is going to be about this minimoon 2024 PT5. And talk number two is going to be about a object with high non-gravitational motion called 1998 KY26. And if we have time, there might be a special bonus at the very end. A very, very recent update. So for the first talk here, I'll talk about 2024 PT5 and exactly what it is. This object that we studied with Gemini. This is a mini moon. It is an asteroid that is temporarily captured by the Earth system's gravity. I'm going to talk a little bit about what a mini moon is. They have many different names. One is natural Earth satellite, NES. One is temporarily captured object, TCO. But I prefer the name mini moon because it's kind of like Mini-Me from that movie. It's not Dr. Strangelove. It's what's it called? Austin Powers. Yes. So there's like a character in it called Mini-Me. So because of that, I prefer the name mini-moon. But basically, mini-moons are these objects which can become temporarily bound by the Earth-Moon system's gravity. Once they're in orbit around the Earth, they have these kind of weird-looking crazy straw-like orbits. So like those toys that kids play with at doctor's offices when they're bored, kind of these loopy things with the beads that go on them. So they have like these very, let's say, irregularly looking kind of satellite orbits. They are captured typically on about 286 days. They have a kind of like a short orbital lifetime, but they can make around, in that time, they can make about 3 revolutions around the Earth-Moon system. And there's also something else we call temporarily captured flybys, a kind of another class of mini-moon where they're captured by the Earth-Moon system, but they only complete like half an orbit. They don't make a full revolution around the Earth-Moon system, and they come in, they're temporarily gravitationally bounded, and they escape again. So we call these temporarily captured flybys. But they're all mini moons basically of some sort, but some are temporary, like very temporary. They're all temporary, but some are very, very temporary, only completing half an orbit on average, but where some actually make a full revolution around, which we call kind of more, let's say, more permanent, or let's say less temporary type mini moon. So mini moons kind of inhabit, if we look at it in kind of a steady state, they inhabit the Earth-Moon system, coming within the Hill sphere around 4 lunar distances, but they can extend kind of outward at quadrature. So this is a plot that is kind of a azimuthal radius diagram showing the time resonance distribution of mini-moon orbits. So this is basically taking all the orbits of mini-moons that are captured by the Earth-Moon system and integrating them in a orbital simulator. And then I'm plotting the average time that they spend close to the Earth. So you kind of get this kind of like egg-like shape where you have this kind of focuses. So here at 0 degrees, 180 degrees, that is directly opposite of the sun and directly towards the sun. So this is where the L1 and L2 Lagrange points are. So they're kind of concentrated here. This is kind of a heat diagram where the lighter colors or more red, more yellow colors have a higher time resonance, and more purple colors have a lower time resonance. So there's kind of like a focus here, exactly opposition where mini-moons tend to spend most of their time in orbit. But this is kind of averaged over millions of cases of mini-moon orbits. This is roughly kind of what it looks like. You get these concentrations at the the L1 and L2 Lagrange points at about 4 lunar distances away from the sun and 4 lunar distances towards the sun. So mini-moons are, we think they're asteroids. We think they come from the asteroid population. I'm going to present some evidence that suggests contrary to that in this talk, but the simulations that I was talking about before assume that asteroids originate from the main belt and then are captured. They come through a variety of different dynamical pathways where they're eventually captured by the Earth's moon system's gravity. So they have a size distribution that more or less falls out of the main belt asteroid population. So this is a size distribution plot, cumulative size distribution plot. On the x-axis, you have diameter, and on the y-axis, you have the cumulative number. So this top line here, we have the size distribution of main belt objects, and the middle line is the size distribution of the near-Earth asteroids. So you can see here that in greatest numbers, the main belt objects, then you have a subset of that which become near-Earth objects. But even smaller than that are the subset which become mini-moons. So the mini-moons kind of fall out of that. So we have this kind of asteroid retrieval mission target population, which are ultra low delta V asteroids. And mini-moons are a subset of that population because to be captured by the Earth moon system, you have to be traveling very slowly, less than 1 kilometer a second relative to the Earth moon system's overall motion.
Is that the total number known at any one time, or is that some accumulation over time?
This is the steady state population. So at any given time, this is the exact.
There are 10,000 ones with a diameter of 1/10 of a kilometer.
So here we have for NEOs, yes, but for the mini moons, it's somewhere on the order of tens.
Okay.
So this is in diameter of kilometers. So something on the order of let's say 1 meter or so. There's a few tens of those in order on the Earth at any time. So I have well, this is a more serious plot, but I have a more funny version of that coming up describing that. But this is specifically the size frequency distribution of mini moons themselves. So when this work was done in 2012, there was only one known mini moon, 2006 RH120. So this was kind of compared to the frequency of that one object. And it was about a 3-meter object. But these are the different possible size distributions of mini moons. And the one that matched back then the observed rate of occurrence of mini moons was this middle line right here, which suggests that there's something on the order of 1 to 10 of these like beach ball size, 1 to 2 meter size objects in orbit around the Earth at any given time. And I have a cartoon here that describes that. So we're talking like half-meter size objects. There's a few dozens of those. And for something that's the size of a washing machine, 1 to 2 meter size, we think there's about 2 in orbit. And if there's something like dump truck size, talking like 30 meters or so, it's like the occurrence is once every 50 years. So this is assuming that mini-moons originate from just the main belt, and they trickle down through the near-Earth asteroid population. They trickle down through that low delta V population, and then you have a subset of that which actually become captured objects. So it's like a fraction of a fraction of a fraction kind of thing. The very first one that I mentioned before is 2006 RH120. It was discovered by Catalina Sky Survey. This is its orbital trajectory around the Earth. It made several revolutions around the Earth. It was in orbit around the Earth for about a year. So it was, yes, kind of a second moon kind of thing. This was about 3 meters. It was actually observed by radar. But back then we didn't have no one actually characterized it spectrally. We just assumed that it had properties similar to that of other asteroids. But when it was discovered, it's actually pretty bright. It's a V19.2 object, and this is kind of sort of a trend as we're finding more mini moons, and they're all being found kind of bright actually, and moving relatively slow. So they're not like other near-Earth asteroids, which are streaking by the Earth at many degrees per day, and are only bright for a very short period of time. Sorry about that. That was my alarm to start the talk. But mini-moons are, because of their capture by the Earth, they're actually moving quite slowly, and they're quite bright. So when they are captured by the Earth, they're actually quite easily detected and easily observed. relatively speaking.
Does that mean they're moving much more slowly than the moon is around the Earth? What is that?
So yes, they're typically moving slower than the Earth because they're
slower.
beyond the orbit. I'm sorry, they're typically moving slower than the moon's motion. Moon's motion is about 12 degrees per day.
Yeah.
But they have orbits exterior to that of the moon. They're typically found at 4 lunar distances, or they can extend out even further than that. So they can have slower sky motion rates compared to the moon, which is great because they're small, something the size of a diving board here in the case of this 2006 RH120 object. And then we have the second known mini moon. This is an object called 2020 CD3. It was also discovered by Catalina Sky Survey in 2020, and it was a few meters in size. So this is its kind of orbital configuration. It has kind of this really wonky orbit. This object was studied by Gemini, by a different group other than my own, but was observed and studied by Grigory Fedoretz at the University of Helsinki. I also observed it as well. So basically, we both applied for DD time to observe this object. They got the time with Gemini. I didn't. So when I didn't get the time, I applied for DD time through Keck, and they gave me the time. And so I took the spectrum with Keck. And what the spectrum shows is that it has a spectrum compatible with this V-type object, V-type asteroid. So asteroids are kind of the 3 main group of asteroids. Kind of speaking here, I'm kind of simplifying this a bit. There's actually many more asteroid types in this, but so you have C types, which are carbonaceous type objects. You have S types, which are more silicate-rich objects, and you have V types, where V stands for Vesta. So there's this huge asteroid in the Maybelt called Vesta, which has its own distinct kind of composition that has a lot of silicate rich material on it. And because of that, it has a very large silicate absorption feature around 900 nanometers. So with C types, they are more or less similar color to the sun. So that's why their spectrum here, this kind of green shaded region, kind of shows the average spectrum of all C types. It's kind of flat. Whereas the S types, is this kind of khaki shaded region here. They have more of a red, sorry, it overlaps with the V types, but has a little bit more of a red slope. And then you have a slight silicate absorption feature at around 900 nanometers. But the V types are even more red slightly more red than the S types. But then they have this huge silicate absorption feature, much more deep than the S types. And so it actually is similar-ish to lunar rock. Both the V types and lunar rock, they both have this huge silicate absorption feature. So what I found with spectrum taken with Keck, because we went to a longer wavelength, we went beyond I band. We were sensitive to the depth of this silicate absorption feature. We find that it has a similar spectrum to V types. Now the thing is, though, is that V types are actually pretty rare in the near-Earth object population. The majority of near-Earth objects are C or S types. So the fact that it looks V type like would actually be sort of a fluke. So it may actually be more reasonable to compare this to lunar rock material, which is this black line right here. So this was the first time anyone had compared the spectrum of a quasi-satellite or of Earth, or like in this case, a minimoon, with lunar spectrum, and found that the most likely case is that it has a lunar-like spectrum compared to asteroids. So the origin of these things could be rather than being captured from the asteroid population, it could actually be captured from the moon as a byproduct of impacts on the moon, as ejected from the surface of the moon during a lunar impact. I'm not going to go into much of the theory behind that, but it seems from the observational evidence seems to support that for this case of 2020 CE3 that it did have a lunar-like spectrum, and I'll talk about that for 2024 PT5 as well. But first, I'm going to talk a little bit about the discovery of 2024 PT5. Yes.
Were the results from Gemini comparable?
So with Gemini, they only got GR and I. So I don't have their spectrum, but it looked very similar going from this green data point R and I. And so there was some communication with them early on. I'm saying, hey, you have to get the Z band, you have to get the longer wavelength than I, because otherwise there's always going to be this debate. Because before that, there were reports of minimoon-like objects being discovered by the ground-based surveys, but they weren't taken very seriously because people would always say, oh, they're just lunar ejecta, lunar material, and we don't need to follow those because they're just some kind of byproduct of impacts on the moon. They're not actually from the asteroid belt. And I was saying, well, I think that's actually really cool. It'd be a really cool thing to test. And we should take minimoons seriously as a approaching them as a test if they are lunar-like or if they're not something from the asteroid belt. But the people who took the GRI imaging with Gemini, I think it was kind of like a they didn't like the people saying these minimoons were lunar ejecta, so they kind of, nah, we don't want to go there with that debate. We'll just take the GRI just to say whether or not it's an asteroid or some kind of other thing floating in the vicinity of the Earth's orbit. But you know, it's kind of a little long story with that. But I was kind of the first to say, oh no, we have to test it. We have to get that C-band imaging so we can see if there's a silicate absorption feature to see exactly if it's from the main belt or if it's from some kind of lunar rock. But in this case, the data actually favored the naysayers, which actually kind of helped the case for minimoons in having people take them more seriously. So there's this new minimoon that was discovered August of last year by Atlas, which is an IFA project. It was discovered by their facility in South Africa. So Atlas, I think I could be wrong here, but I think they currently have 4 facilities. They have one in Mauna Loa, one in Haleakala for the northern hemisphere, and in the southern hemisphere they have one in South Africa, and there's also one in Chile, sort of near where Gemini South is. It's in the vicinity of the Gemini South site. I don't think it's on Cerro Pachon, but it's like within like 10 kilometers of Cerro Pachon. Someone can correct me that if they know better the Atlas, but this was discovered at the South African site by Atlas in 2024 of August, and it had sorry, I don't have the V magnitude on here, but it has a V magnitude around 19. So this is you can see it's trailed here in this image. It's because its motion is fast enough for it to become trailed in the 40-second exposures of the Atlas survey camera. So this object was a temporarily captured minimoon. It was captured about 60 days between September and November, but it did come within the Hill sphere of Earth. So this is kind of an orbital diagram showing the X and Y Cartesian coordinates centered on the Earth's location. So the Earth is at the origin of this, and the Hill sphere of the Earth is this kind of green shaded region. And so the minimoon came within the Hill sphere of the Earth and was captured in this kind of orange, this kind of red portion right here. So it had an eccentricity for about an Earth-centric eccentricity less than 0. I'm sorry. No, that's a typo. This should actually say less than 1. No, actually, this is energy. Sorry, this is not eccentricity. This is energy. So it had a relatively relative orbital energy of less than 0, but it had an eccentricity of less than 1 in this green portion. I'm sorry, in this red portion right here. So it basically means, from the perspective of the Earth, it had an orbit that was not hyperbolic. It had an orbit that was a closed ellipse. So it was, in a sense, a captured object, even though it did not complete a full revolution around the Earth before leaving it again. But for that period of time, its orbit had a temporary eccentricity of less than, with respect to the Earth, of geocentric eccentricity of less than 1. So I applied for a fast turnaround time to observe this object because it was going to be observable long enough that the fast turnaround time turnaround scale worked perfectly. So I applied for time. I think it was in the September call, so it was like due around August 30th. So so within a few weeks of the announcement of the object, I submitted my request, and it was accepted, and it was the observations were executed very quickly. A few days after I got the notification email for the acceptance of the program, and the data are quite exquisite. So I got GRI and then capital Z. This is not lowercase z. It's capital Z. So it's similar to SDSS band, but it kind of cuts out some of the terrestrial features. So it's actually a more clean image. You don't have as many. You don't have the pattern that comes from the terrestrial effects of the Earth's atmosphere. You don't have the fringes. Fringe removal is much more cleaner than if using the lowercase z band. But it still gives us the great coverage in that spectrum going past I band that allows you to test the silicate absorption feature depth. So I'm going to show you the colors first before I show the spectrum. So in color space, this is a plot showing the colors compared to other of the minimoon 2024 PT5 to other asteroids in the solar system. So the x-axis here is A star, and it's basically a function of G, R, and I. It's more or less the optical slope between GR and I. And the y-axis here is I minus Z, which is the difference in color between it's the color between I and Z band. So that gives you kind of silicate absorption features. So just to kind of illustrate the importance of Z band here is that with GR and I, you can tell where stuff falls on the x-axis of this plot. So the division line here between S types and C types is somewhere around 0 A star. And so the blue stuff right here, those are all C type, the carbon-rich asteroids, and all the stuff on the right here is the more silicate-rich asteroids. So if you just had GR and I, you could tell the difference between C and S type. But you really need the I minus Z, because when you plug that in here, you get the difference between this red stuff and this green stuff, where the red stuff right here are the S types and the green stuff are the V types. So that's what really lets you test if the object is an S type or a V type by the depth of that silicate feature. And so the colors of the various different asteroid groups, the mean colors is here. So you have for C types, the C-type asteroids are located right here. The uncertainties are quite small because this is based on spectroscopy, whereas all these data points here are based on SDSS photometry. And right here, this blue cross right here is the average color A star versus I minus Z of S types. And for the bulk V type is this purple cross. And then for bulk, I threw in lunar rock there. Is this kind of orange. So the lunar rock has a deeper silicate absorption feature than even the V types, and it's definitely on the right side of this plot. The mini moon right here, I put right here. It's this red cross right here, so it's definitely has a silicate absorption feature deeper than the S types. But here's the actual spectrum. So one thing to note is that the GRIZ data points, they have a higher slope than the V types. Than most V types, but their silicate absorption feature is not as deep, I would say, but it's certainly deeper than all of the known S types. We use SV here because it was the closest match S type. So the fact that it's S sub V, so it's somewhere between the closest match with a known asteroid type is S sub V. So it kind of tells you that it's leaning more towards a V type. But the actual closest spectral match is actually lunar rock. Is this black line right here. So it compares most favorably with lunar rock compared to all known asteroid spectral types. So we think we also were able to measure the density of this object based on the perturbation on its orbit from solar radiation pressure, and it has a density as well similar to lunar rock. So we think with those two independent kind of lines of evidence that this is an object that originates from the moon, and it's the second known mini-moon to show this. So it could be that the population of mini-moons is dominated not necessarily by capture from the NEO population, but it could be from lunar ejecta itself. It could be that the moon is the dominant source of Earth quasi-satellite-like objects. We also were able to attain the rotational light curve. So we got a 40-minute rotation period. So it's pretty small for an object of this size. But really what this light curve tells us is that we get about a quarter mag amplitude. So tells us that it's a non-circular shape. But though there is some recent evidence that it might be tumbling, there's another group that is studying this object with telescopes in Japan. And they say that they are able to see something that looks like a periodic light curve. But they get a rotation period that is a little bit different than ours, and it could be changing their actual rotation period as measured from the light curves compared to over multiple light curves taken over a large amount of time, could be changing, indicating that it's a tumbling object, non-principal axis rotator. And that seems to support that it has a very recent collisional origin, that it's a piece of lunar material that was ejected from the moon's surface. So that's all I'm going to talk about for Minimoon 2024 PT5. I will tell you, there's a really interesting paper by Rob Jedicke at the Institute for Astronomy, and he's actually simulating the ejection of lunar material from the lunar ejecta from the moon, and comparing that to the observed Minimoon population. And the evidence so far is tentative, and the paper is still going through review, but the results so far look pretty interesting as far as supporting evidence that the Minimoon population is dominated by lunar ejecta. So now I'm going to talk about high non-grav asteroid 1998 KY26. Now this asteroid has a little bit of an interesting story because it's one of the smallest near-Earth asteroids to be characterized of all time, but it also happens to be a target of the Hayabusa 2 mission. So Hayabusa 2 is a Japanese mission that visited asteroid Ryugu, and they had some leftover fuel, so they're actually going to go to this asteroid next, and it's going to rendezvous with this asteroid in 2031. So I'll talk a little bit more about that. But more interesting thing about it, or equally interesting, I should say, is that this object has high non-gravitational accelerations, and I'll talk a little bit about what that means. So the high non-grav asteroids have another name in the literature called dark comets, but I don't like that name because it presumes that the acceleration of these objects is caused by the sublimation of volatiles, because comet is something that is outgassing like water vapor or CO2. And so calling something a comet presumes that this object is outgassing. And so even though there's no evidence of that at all. So I'm going to call these high non-grav asteroids. It's not a very, let's say, easy name. It's not as easy to say as dark comet, but it's more, let's say, I would say it's more accurate to what I think these things actually are. So these so this is a plot showing the acceleration, the non-gravitational acceleration of these high non-grav asteroids as a function of the absolute magnitude. So the absolute magnitude here is on the x-axis, and as you all know, is that the smaller the higher the number, the smaller the object is, and the projected diameters on the equivalent diameters on the top x-axis here. So this is showing these asteroids between 10 kilometers size all the way down to about a meter size. And so the y-axis here is the acceleration in AU per day squared. And if we include just the Yarkovsky effect here, so the Yarkovsky effect is a thermal recoil force, where as an asteroid is rotating about its spin axis, the day side is becoming heated by the sun, and when as the asteroid is rotating, when it's that part of the asteroid is heated up, that it reaches the afternoon side, the thermal emission of the photons actually imparts a non-negligible momentum that can actually accelerate the orbit. So I call this thermal recoil force, or the Yarkovsky effect. However, there's a subset of these objects which have non-gravitational accelerations well in excess of the Yarkovsky effect. So even taking into account the Yarkovsky effect, they had non-gravitational accelerations that are or even higher than that. So you have to have an explanation, okay, is that it's not thermal recoil force. There must be some additional effect going on here that is accelerating these asteroids even more so than the non-gravitational rate. They can also have radiation pressure can be an effect here, but for large asteroids, it's hard to move something on the order of 10 meters or more. It's hard to move something that big with total radiation pressure. It implies like a very, very low density. So we're getting back to the famous Oumuamua debate, because Oumuamua is another one of these non-grav asteroids. Oumuamua was observed to have a very peculiarly large non-gravitational acceleration, and there were two explanations for it. One, it could be outgassing, so it's there's some kind of outgassing that is pushing it, like kind of like a rocket force, or it could have a peculiarly low density. And so if you assume that the Oumuamua is a 200-meter size object, if you assume that its non-gravitational acceleration was due to solar radiation pressure, it would have a density of like 10 kilograms per meter cubed. So that's like, like rocket cellophane material, or like something very, very hollow. And so that's what caused Avi Loeb to speculate that it was like some kind of alien spaceship or rocket parts or something like that. Yeah, and that's going off some very, very different direction than usually what I discuss here. So the more natural, let's say, explanation is that it was some kind of rocket force from the outgassing of volatiles that were in the object itself. But it's sort of like a similar debate here, is that we observe these objects that have peculiarly large non-gravitational accelerations, and it seems that solar radiation pressure isn't an accurate enough description for that, because it would imply that these objects have very low densities, like much lower than solid rock. So there must be some other mechanism here that is causing these objects to accelerate. So the recent publications by Seligman and Davide Farnokia, they claim that, okay, this is has to be due to outgassing of water. But I don't think that's the case. And so when this object became observable this summer, I applied for director's discretionary time to observe it. Oh yeah, another thing is the reason why they're called dark, when they're called dark comets, is because they don't have a tail. So this is 3,200 80 seconds exposure taken at VLT with the 4.2 camera and open filter. So no filter at all. So it's even more sensitive. And this is of object 2003 RM. And so you can see here, even in this very deep image, it does not have a variant. There's no appearance of a tail. On the right-hand side of this plot is the azimuthally averaged surface brightness profile compared to a star, which is the solid black line, and the object itself, which are the dotted black points. And they're basically the same. Where if this object had a tail, the object would have an increase in the surface brightness profile once you get outside the point spread function. For this object, it's about 1 arcsecond seeing. So once you get out beyond about 2 arcseconds or so, if there was a tail, you could start to see it. But when you see here in the corner of this plot, that the surface brightness profile, even out at as far as 2 arcseconds, really does match the star itself.
So it's, I mean, it's outgassing like a comet, but it's not enough to produce a detectable tail. Is that what you're saying?
Well, that's the thing. It's the weird thing about these things. In order to explain the accelerations that you observe, you have to have a sizable amount of mass loss in the form of outgassing H2O. And you have to have a ludicrously low dust to gas ratio, like much lower than anything we've seen in the solar system, to explain that mass loss needed for that acceleration and not produce a tail.
Yeah.
So I think there's something else going on here, and I'll talk a little bit about that. So my approach to test the mechanism of dark comets is to use multiple lines of evidence from their spectral characterization as well as their dynamical origins. So in this paper, that was just submitted to AAS Journal, so it's under review. I computed all of the likely origins. Sorry, this is a very ugly way of presenting this information. I'm sorry, I'm showing you a table, but this table shows for all dark comets what the probability, their relative probability of originating from the main belt is, as well as from the Jupiter family comet population. So I have here on the most left-hand side column, this right here is all the currently known dark comets. And ignore these next few columns here, but focus on this one right here. The P sub Hun, P sub nu 6, P sub PHO, P sub 3 to 1, P sub 5 to 2, and so on. Those are the probabilities that these objects originate from the Hungaria population, the nu 6 resonance in the main belt. And I'll talk a little bit about what that is exactly. The Phocaias, the 3 to 1 motion resonance, the 5 to 2 motion resonance, and the 2 to 1 motion resonance, and finally Jupiter family comet population. So if you look at this second column right here, the nu 6, the dominant source for the vast majority of dark comets is the nu 6 resonance, as well as the 3 to 1 resonance. So these are located very, very close to the sun, the most interior part of the main belt. And so I'm going to show you exactly where that is. And by the way, 1998 KY26 is exactly that. The dominant source is a nu 6 resonance, as well as also the Hungarias, which is kind of interesting because I'll talk a little bit why that's important. But basically, to illustrate where the most dominant sources of the dark comets are in the main belt, I'm going to show you this plot here that shows the location of asteroids in the main belt as a function of their semi-major axis here, which is on the x-axis. It's a 2-panel plot. So both the top and bottom panel plot have for their x-axis the semi-major axis. And on the bottom panel plot, you have eccentricity, which is the elongation of an orbit. And on the top top panel's y-axis, you have sine of the inclination, which is the angle between this asteroid's orbit and the ecliptic. So we can see here that the 3 to 1 resonance is located at 2.5 AU. That's kind of exterior to the most inner part of the main belt here. And then you also have the nu 6 resonance, which is a resonance that is defined as a function of semi-major axis, and it's the location of it changes as a function of semi-major axis by its inclination. So if on the most inner edge of the main belt, the location of the nu 6 resonance has very low inclinations, but as you get towards the outer part of the main belt, the inclination gets quite higher.
the location of the resonance is at much higher inclination. So that's why it kind of carves this gap here, because asteroids located along these resonances are unstable and can be transported onto Earth terrestrial planet crossing orbits, or even with Jupiter itself, and are depleted. So over time, it creates this kind of gap. But where the near-Earth asteroids that are these dark comets originate are from these locations. So it tells us that they must come from very, very close, relatively close to the sun, and not the comet population. So they're not comets. They're actually asteroids that originated from the inner portion of the main belt. And I don't have it marked here, but this region right here, these are the Phocaias. There's another group of asteroids called the Hungarias, which are interior to the main belt inside of 2AU. I don't have it plotted here, but they're even closer to the sun. But the point is that the majority of dark comets originate from this region of the main belt, vary between 2.2 AU and 2.5 AU. And that's very important because we have evidence from various chemical evidence that suggests that the ice line never retreated any closer than about 3 AU. So all asteroids interior to here kind of, let's say, dried out. They shouldn't have volatiles on them. And so evidence for that, you can actually see that evidence for that in another population of objects called active asteroids or main belt comets. So it's kind of a similar problem. So main belt comets are this category of asteroids which are in the main belt that have like a comet-like appearance, have a comet-like tail. And it's there was kind of a similar debate that was occurring about 10 years ago. What is driving the activity of the main belt comets? And over a decade of studying these, we can actually group these into two different categories. We now call them active asteroids because it's kind of more, let's say, accurate to their description because they're not actually comets. But the things that are driving the activity of the main belt comets falls into two different categories. So we have category of active asteroids whose activity is driven by non-sublimation mechanisms, which are these red squares here. And there's another category of active asteroids whose activity is driven by the sublimation of some kind of volatile, which are these green circles right here. So these are, so in the, let's say you have, in this overall like umbrella term, active asteroid, you have a subset of population which have their activity that is not driven by volatiles, which are just normal active asteroids. But then you have another part of the population whose activity is driven by the sublimation of volatiles, which are actually the true main belt comets. So you can see here that in this plot, there are no sublimation-driven main belt comets really inside 2.5 AU, really like somewhere around 2.7 AU. But the closest true main belt comet is around 2.7 AU. But inside of that, there are no sublimation-driven active asteroids. Now, this was written around 2022. It's like small number statistics as far as objects go in the inner main belt. But it seems to suggest that for the dominant source of these quote-unquote dark comets, that they come from a region of the main belt where there's not actually any volatiles. It's actually a very dry part of the main belt. Therefore, it seems that the activity, as evidenced from the non-gravitational acceleration, is not due to the sublimation of volatiles, but it has to be due to some other mechanism other than volatiles.
How do you determine again whether it's sublimation or non-sublimation? Is that from spectroscopy or?
Yes. Do y'all have here? I can draw a place. Okay, if I draw on this.
Yeah.
So spectroscopy has not been possible until very recently, until the advent of the James Webb Space Telescope, because the James Webb Space Telescope allows you to directly detect water vapor from at wavelengths that are inaccessible from the ground. But as this topic has been going on for decades, the way they have done it classically, which is now starting to be confirmed by James Webb observations, they're actually starting to observe some of these green objects by James Webb, and they actually see water vapor emission at 2.77 microns.
Okay.
Which is inaccessible from the ground. So how they were doing it classically, spectroscopically, is they would use things like Gemini, they would use things like Keck, and they would look for the byproducts of water vapor emission that are evident at shorter wavelengths. But the mechanism to transform water vapor to these other byproducts is very inefficient and very difficult to detect. So you really have to detect it directly at the source of the water vapor source, which has not been available till couple of years ago with the advent of James Webb. But the other way of doing it is by looking at the occurrence of activity as a function of perihelion distance. So I'm going to try to draw an orbit of an asteroid right here. So bear with me. But let's say this point right here is the sun, and you have an asteroid's elliptical orbit looks something like this. So this direction right here is the perihelion direction, which I'm going to call Q, because Q, lowercase q, is typically the symbol for perihelion. And so for the active asteroid objects whose activity is driven by the sublimation of volatiles, the onset of activity is typically seen somewhere as the asteroid is approaching perihelion, because the sublimation rate of water increases exponentially with heliocentric. The closer you are to the sun, the rate of sublimation increases exponentially. So it's kind of a circumstantial argument that, yes, we see the onset of activity is starting to occurs when asteroids are closer to the sun, near the perihelia, where when they're observed at aphelion, you don't see any activity. However, the more mechanically driven ones, the ones whose activity is not driven by water, you see the onset of activity is quite random. You'll see something like this. I'm going to use a different marker here. For the mechanically driven case, you'll see onset activity at aphelion, or it'll be a quadrature. You might also have somewhere randomly, by chance, it could be at perihelion as well. But the point is that it's not correlated significantly with perihelion distance. So it's kind of a circumstantial evidence. So they divide into these categories. Over decades of observations, they've observed when these objects have become active somewhere around their orbit. And so they can circumstantially divide these into different categories. If they have kind of a random distribution, it's the mechanically driven ones. Where it's correlated with perihelion distance, it's the sublimation driven ones. So now James Webb, there's 3 objects that have been studied, James Webb, that come from this perihelion correlated one, and they have water vapor emission. So kind of a smoking gun. Yes, finally, we know that these Q correlating ones are actually true main belt comets, like true comets in a sense. But for these dark comets, I'm not convinced that the evidence is there, because there can be other mechanisms that can explain their non-gravitational acceleration. I'm still going to take the circumstantial approach here. This is a combination of Keck and Gemini here. So we got spectra with Gemini, which I'm going to show, but we also got deep imaging with Keck and GNR. So this is a combination of GNR from the LRIS camera, 720 seconds. So yes, it's not very deep, right? But the point is that this was taken on June 8th when this object was 10 lunar distances from the Earth. So it was the closest that this object had passed by the Earth than has ever been observed before. And between now and, between then and when the asteroid is encountered by Hayabusa spacecraft in 2031, there are no available corridors to observe this object again from the ground. It's way too faint towards solar elongation. So this object had to be observed by Gemini and Keck. I actually submitted a DDT with Gemini, and we were able to observe this on June 8th and 9th. But this is the deep imaging from Keck using the comparison with the like a kind of a reference star. Does not show any evidence of an extension. The angular, so I hypothesis as a function of the surface brightness is a function of angular radius. The pixel scale here is about 0.27 arc seconds. So we get to this is showing at about showing the angular scale from about 0.27 arc seconds all the way out to 2.7 arc seconds, and there is no deviation from a stellar object in the brightness of this 1988 KY26 object. So this actually allows us to constrain the mass loss of this object to within about 10 to the -5 kilograms per second to about 1 kilograms per second. And the reason why that is because we don't actually know the dust properties. We don't actually know the size of the dust. Depending on the size of the dust, you can have very different dust mass loss. But the point is that if you assume the ejection velocity for something that is very loosely gravitationally bound, like barely the escape speed of this object, leaving at about a few centimeters per second, that in order to explain the observed non-gravitation of this object, you'd have to have a mass loss for centimeter-sized particles of about kilogram per second. So this is a spectrum from Gemini. It's very, very telling because when we compare it, the closest match that we get to all the asteroid spectral types is XE type. The closest match is XE type asteroids, the majority of which originate from the inner main belt. So we have the dynamical evidence that shows that this object originates from the inner main belt, and now we have the spectral evidence showing that this is an XE type, which are classically known to not show any hydration features. They're some of the driest objects in the solar system. That these two different lines of evidence suggest that this is not a comet. So comet spectra typically look like D types. This kind of orange shaded region right here. They have very, very red slope. This object does not have slope anywhere approaching that of a D type. The closest match is XE type. So I think because of that, it's the mechanism that is driving the activity of this object is not the sublimation of water. It has to be due to some other mechanism, which I speculate, don't have any direct evidence of this, but I suspect it has something to do with its rotation. So this asteroid is actually spinning so fast, as it has a rotation period of about 10 minutes, and that's much faster than the asteroid to spin for small grains of material to remain gravitationally bound to its surface. So I think it's sporadically releasing pebble-sized objects into space, and that loss in mass is causing an impulse on its orbit to explain its non-gravitational acceleration. But we'll see. Hayabusa 2 will get there in 2031, and it will be able to detect dust mass loss well below sensitivity of 1 kilogram per second. Like we're talking 10 to the minus 9 kilograms per second. So
say acceleration could be deceleration too, could it not, or is it just acceleration?
So for this object, so the three different components that describe the acceleration of this object, they are positive in the radial direction and in the transverse direction, but they're negative in the planar direction. So that means that the emission must be occurring in the positive direction, which is causing it to displace itself more towards the negative direction. And that's in terms of the direction of its orbital plane. So within its orbital plane it wants to accelerate in the negative direction with respect to its orbital plane. So in the negative outer plane.
Which way is it spinning relative to its orbital direction?
We don't know. We don't know the spin vector. I suspect that it could be it could be retrograde because it's in the negative direction. It could be retro. It could have a retrograde obliquity.
And they're all like that. The ones that.
So not all the main belt comets. Oh, sorry, not all.
The ones that are accelerating or decelerating.
They're not all like that. No. But they do have a lot of them do have significant out of plane accelerations, which is another reason why people were speculating that they were comets because the Yarkovsky effect is in the transverse direction, radial the solar radiation pressure is in the radial direction. So for something to be out of plane would seem to imply you'd have to have some kind of like comet gas jet or something. But what I'm showing is that the physical properties and the dynamical properties of these objects have nothing to do with comets. Yeah. So there's something else going on here, and they're coming from a region of the main belt where there are no main belt comets. So it's not some other these aren't fragments of the main belt comets. They come from too close to the sun for that to be the case. So I think our knowledge of the possible, let's say, activity mechanisms of these things cannot explain in terms of the interpretation of the cometary outgassing model, cannot explain the observed non-gravitational acceleration of these objects. So this is again, so this is like showing the location. Yes.
Yeah, 5 minutes.
Oh yeah, I'm almost done.
Okay.
So this is again showing the location of where XE types are in the main belt. So these are called XE types in this plot are called E types. So the majority of them are located at 2 AU, much further, much closer to the sun from where D types are located, like the classic cometary D or P types, the classic cometary taxonomic classes. Most of the main belt comets tend to be C types, by the way. But the E types are much displaced from that. So when looking at like the spectral, like doing this kind of spectral method shows very convincingly that these are come from a location in the main belt, much more different from where the majority of the comet-like objects come from. Okay, so this is a bonus slide. I'm going to talk about potential impactor 2024 YR4. This was another Atlas discovery from Chile. This is an asteroid about 50 meters in size that was discovered on a couple days after Christmas 2024. And as of now, as of today, it has a 1 in 45 chance of hitting the Earth in 2032. And so it's receding further from the Earth right now. So it's becoming more and more difficult to observe and will not be observable again until 2028, which by then we may not know, we may not have eliminated the possibility of this thing having a non-negligible chance of hitting the Earth. So therefore, in order for us to understand this object and to understand better constrain its physical properties, it's imperative for us to observe it now, which we did with Gemini. We got director's discretionary time at Gemini South. These are images that were taken just a few days ago on February 7th. The Catalina Sky Survey team helped me out with this. They made this stack and measured the astrometry of this object. And this is the killer asteroid. It's very small, so don't worry about it. But yeah, that's it right there. Gemini South R band 12 200-second images. So it was about 23.7 magnitude there. And with our observations, we refined the orbit such that the impact probability went from 2.4% to 2.2%. So as a result of our observations, the impact probability, we might be weakening the case that this could hit the Earth. However, this object is observable for like the next couple of weeks by ground-based observatories. It's going to be observed by JWST, I believe, in late March, which will further refine the orbit, which may increase the probability or eliminate it altogether. We don't know yet, but we're helping out here. So here is a summary with QR codes that lead to the papers. If you want to check them out. Sorry, the labels here are wrong, but the QR codes are accurate. So the minimoon one has been published in AppJ Letter. It's in this purple QR code. It was published in AppJ Letters in January 7th of 2025 this year. And the 1998 KY26, the high non-grav object, is in this blue one right here, which is currently under review in Astronomical Journal.
We have time for 2 short questions or 1 long one. Also online if you want to raise your hand.
I have a short question. Is it very difficult to take like actual spectra of these mini moons?
They're very faint.
Okay.
Yes, so they are so this PT5 object, when we observed, so it was discovered about 19, but it was revolving. It was sort of orbiting the Earth then. So the viewing geometry was changing quite a lot. So it was discovered when it was at its brightness, and a few weeks later, the faintness, the brightness increased all the way to 22 and a half. And if it was a stationary object, yes, I think it would be really easy to do spectrum. But because these things are moving so relatively quickly, it's hard to do like a blind offset or anything. So and the positional uncertainty is from the ephemeris can be order of arc seconds. So that can make acquiring it and centering on the slit rather difficult. So I just prefer to get the imaging. But if they are bright enough, if they're brighter than 20th, then yeah, 21st, and I think for these things. Now this is this 1998 KY26 that is spectroscopy. I believe the object was a little fainter than 20th magnitude, and it was a heroic effort by the Gemini staff. That was a very difficult observation because in 15 minutes the object was moving 3 arc minutes. So we had to lower the exposure time so that we could keep the guide stars in there. And it was going through a crowded star field as well. So we took 6 exposures, 600 seconds, 4 of which were not collided with a star. So it was a heroic effort. The team knew very well how to observe asteroids. And they also used a wider slit. So we used a 1.5 arc second slit. The seeing was really, really good. The seeing was 0.4 arc seconds. But that was very good for the asteroid because if you have any positional if you don't capture the full point spread function of the asteroid, if the slit's too narrow and it's not position on top of the asteroid, then you're going to get all sorts of problems in your spectrum. It's not going to be as reliable. So it was like the perfect asteroid observation. Very difficult target. So yeah, thank you to your support because it was your skill that made these results possible.
Thanks.
I have a quick question. So how does I think almost all the slides that you presented today were all in the optical, talking about optical data.
Yes.
How does near-infrared data help inform the interpretation? You're observing the atmosphere, I guess, coming up soon.
Right. So near infrared helps out a lot because the differences between the asteroid spectral types are even larger in the near infrared than they are in the optical. But near infrared is a lot more difficult. It's near infrared near infrared observations are in general more difficult than optical light. So what I'm hoping to do with like these deep imaging with the infrared using these infrared cameras is to extend the spectral coverage from just the optical wavelengths all the way out to 2.5 microns, where the difference between the spectral types is larger. With Mossfire, though, I'm not observing these type of objects. I'm observing outer solar system objects. I'm observing these objects called Neptunian Trojans, which are asteroids in a 1-to-1 mean motion resonance with the planet Neptune. And the spectral coverage in the infrared helps us see all these weird features that are now being evident thanks to James Webb in the spectrum of these Kuiper Belt, of these trans-Neptunian objects. We see all sorts of weird stuff going on there that you don't see in normal asteroids closer to the sun. But even for asteroids closer to the sun, having the near infrared is great. It's not crucial. It's not crucial like it is for the Kuiper Belt objects, but it helps out a lot.
We reached the top of the hours, but you will be here around until you talk with kids.
Yes.
So
Yeah, they are coming at 1, I think. Okay.
They're arriving at 12:45. We'll probably be in here at 1. We can talk more.
Sure,
Yeah.
sure. Yeah.
so
So
more question, you have a nice lunch break. Otherwise, see you next time. Thank you again.